I'll just give it a minute. Yeah.
Compilation I use has you can get it down to log of n squared. Log of n squared. Oh, so does it have to?
Okay, so our next speaker is William Kretchmer, who is at UT Austin. William was a postdoc here at the Simons Institute, and over the last 2 years as a postdoc, his work is in quantum complexity theory. Very abstract, but over the last 2 years, he's worked with people at Quantinuum on this experiment he'll tell us about.
Yeah. All right, yeah, thanks, Umesh. So this is based on a collaboration with people that are all currently either at UT Austin or at Quantinuum, but like Umesh said, a great fraction of this work was completed while I was a postdoc here up until a couple of months ago. And it's just a good example of the kinds of, I guess, collaborations that can go on between the Simons Institute and industry. So I guess to get things started, so one of the most striking features of quantum mechanics is that if you have a system of n particles or a system of n qubits, then quantum mechanics predicts that the state of that system is described by a vector in an exponentially large Hilbert space. So a vector with like 2 to the n complex amplitudes, which in particular means that if you want to write down a classical description of a quantum system, then it would appear that you need something like 2 to the n bits to describe such a system. And this exponentiality of quantum mechanics is one of the sources of its believed computational power. So the fact that you need to sometimes write down an exponential description is kind of why we believe that quantum mechanics is difficult to simulate. But it is also a continued source of skepticism of people who don't believe that quantum mechanics or quantum computation are real or possible in principle. I doubt there are many such people in the audience today, but you never know. And I guess kind of the starting point for this work is this really basic question of can we somehow test this and actually prove that you can generate quantum states of sufficient complexity to access this exponentiality of Hilbert space? And if we look at how kind of experiments that have probed this question to date, maybe the most relevant experiments are those demonstrating quantum computational advantage, or quantum supremacy, it's sometimes called, which started in 2019 at Google, and we've since seen several better and better experiments that have built bigger quantum computers with better fidelities. But I guess one of the downsides of many of these experiments, and one of the limitations of them, is that in each one of these experiments, the quantum computational advantage is conditional. So it depends on computational hardness assumptions that we don't know how to prove, basically that these experiments are hard for classical computers. And in complexity theory, it's in general really hard to prove things. And so skeptics can say that, well, we don't actually know how to show that these computers are doing something that classical computers can't. And indeed, this is not just like a theoretical worry. We've actually seen like a couple of papers that have, by developing better classical simulation algorithms, have at least, if not completely refuted claims of quantum supremacy, have at least put them into some reasonable doubt. So this sort of raises a question of whether you can get around this sort of computational hardness. Yeah, what's the question?
What's the difference between the question you're interested in and something like Bell's test?
Good. So Bell's test, while it does test quantum mechanics and some properties of quantum mechanics that are not shared with classical mechanics, a Bell inequality violation does not test the exponentiality of quantum mechanics. So it tests non-locality, but it does not test the size of the Hilbert space. Yeah, so in some sense, I guess what we're hoping to do in this experiment is basically this. We just want to do something with n qubits that we can sort of prove would require much more than n bits. And we want this to be unconditional, and we want it to be niscable. So we want it to not rely on any unproven computational hardness assumptions. And of course, we want to be able to demonstrate this on a near-term device. And we don't necessarily care about computational infeasibility. We just want something where we can show that provably there are quantum states that you can generate that could not have succinct classical descriptions. And this is exactly what we did in this work. So the main result of this work is an experiment that we demonstrated using 12 qubits, where we can prove that replicating this using classical information resources would require at least 62 bits. So I guess 12 versus 62 is a pretty modest separation, but at least to our knowledge, it is the first unconditional separation of its kind. And one thing I should really emphasize is that this is not a separation based on computational hardness or computational infeasibility. So we are not claiming that we solved a problem on 12 qubits that was infeasible for classical computers. The relevant measure of complexity here is really, I guess, information content, or you can think of it as storage. So we show that there's some sense in which you can store something into 12 bits such that if you wanted to replicate this using classical memory, then you would need a RAM of at least 62 classical bits. And what I'm going to do in the rest of this talk is say a little bit more about what we actually did and what was the actual task that achieved the separation and how we implemented it. So let me start by telling you a little bit about the basic setup of this experiment and how you would hope to test something like this. So I guess here's maybe how you could imagine testing this prediction that quantum states require 2 to the n bits to describe. So imagine you did an experiment like this. You start by generating some 2 to the n bit string, some 2 to the n bit file. And then you run some sort of quantum compression algorithm to, I guess, compress this into an n-qubit quantum state that you store in your n-qubit quantum hard drive. And then later, at some time, you kind of run this process in reverse. You decompress your n-qubit state back into a 2 to the n bit file. If you could do something like this and repeatedly do it and show that you're continually succeeding in, I guess, compressing and decompressing a 2 to the n bit string, then that would be pretty convincing evidence that the quantum hardware in the middle actually requires 2 to the n bits in order to describe it. Unfortunately, there's this result known as Hilbert's theorem that essentially says this is impossible. And in fact, what it says is that as far as information storage and retrieval is concerned, qubits are no better than bits. So if you want to store n bits of information, then you can't do that using any less than n qubits. And so if you somehow want to show that there's some sense in which n qubits are storing a state that is more complicated than what can be stored using an analogous amount of classical information, you need to do something beyond this kind of task of just storing and retrieving the entire message. But it turns out that this setup is not too far away from something that you can do that actually does achieve a separation between quantum and classical. And what you have to do to change this model is kind of change the task at the end just very slightly so that instead of trying to recover the entire 2 to the n bit message, your goal instead will only be to recover some partial information about the 2 to the n bit message that perhaps depends on a query that will come to you at a later point. And just to give kind of a canonical example of something that would fit into this framework, you could imagine that at a later point, someone comes along with an index I, a number between 1 and 2 to the n, and they just say, please tell me the ith bit of this message. And now, since you're only trying to recover 1 bit of the message rather than the entire 2 to the n bits, Hilbert's theorem no longer applies. And in this setting, you can start to have separations between quantum storage and classical storage in a provable sense. So we've actually known for actually over 20 years at this point that there are tasks in this setting that you can solve using n qubits that provably require an exponential amount of classical information in order to replicate using classical RAM. I should note that the task achieving the separation is not, exactly this task of just recover a single bit of the message. It's something more complicated, but it does fit into this basic framework of you turn a classical string into some quantum state, and then you wait some time, and then based on a query that comes to you at a later time, you try to recover some information about the state. So great. So essentially, our proposal is to take this and demonstrate it. And I guess what you should be asking yourself at this point is, I just said we've known about these types of separations for about 20 years. Why hasn't anyone done this before? Why are we kind of the first to do this? And there's actually several, I guess, limitations that had to be overcome in order to make this a reality. So the first is one of actually obtaining the sharpest possible separation between quantum and classical. So if you look at the best separations that were known, which are usually formalized in a framework known as communication complexity, the best separations between quantum and classical communication complexity were something like n qubits versus omega of 2 to the n over 2 bits. And we really want to improve this both by, first off, if we can make that exponent bigger, if we can go from 2 to the n over 2 to just 2 to the n, that's a quadratic improvement that even at pretty small n can make a huge difference. And two, we really want the constant inside of that big omega to be explicit and reasonable, right? If c is like 1 over a billion, then n has to be pretty large before c times 2 to the n is bigger than n. A second, I guess, limitation or a second difficulty that one has to account for is noise. So the simple fact that today's quantum devices are not perfect. And in your lower bound, when you're showing that classical algorithms could not spoof this unless they had a large amount of memory, that lower bound also has to account for the noise rate of the quantum device. So if your quantum device is only succeeding with some probability p, then you need to show that any classical algorithm that succeeds with that same probability still has this sort of exponential lower bound on the amount of memory that is needed. And then finally, I guess the last reason why this hasn't been done is that, frankly, up until recently, the hardware really was not good enough. And the hardware that we used for this experiment was built at Quantinuum, their H1 trapped ion computer, which uses about 20 qubits. And what turns out to be kind of the most crucial parameter for whether you can do this type of experiment is the entangling gate fidelity. So Quantinuum can do basically 99.9% fidelity, ZZ rotations, which is their native entangling gate. And that turns out to be good enough for this experiment. I guess another nice feature, even though it's not like strictly crucial for this, but it was helpful, is not really having to worry about connectivity. So on trapped ions, it's very easy to do all-to-all gates because you can move around the qubits quite easily. Good. So why don't I move on to talking a little bit more carefully about what is the actual task that we solve in this framework. I mentioned that there's a way to phrase this in terms of communication complexity, but I think I'll stick to talking about it in this model. And in some sense, the task that we solve is kind of, in a way, like the most natural task that you can consider, or most general that you could consider in this framework, where you kind of make everything as random as possible. And OK, what do I mean by this? So the input will be, you start out with, I guess, just a description of an n-qubit quantum state. That is the classical message that you start with. And you will turn this into, I guess, preparing that quantum state on your quantum computer. And then the query that will come to you later is someone will ask you, they will give you an n-qubit quantum circuit C. And your task will be to output a measurement that is consistent with the output distribution of this quantum circuit C applied to that quantum state psi. So this will be some n-bit string, which we will label as Z. And the output, I guess the condition that we want on the output, so we don't want the measurement to just be an arbitrary result. We want it to somehow be consistent with quantum mechanics. And actually, the test that we do is this one. What we want to test is that if you look at the ideal output probability with which this string Z would have been output on the circuit applied to psi, you want this ideal output probability to be non-negligibly bounded away from 1 over 2 to the n. And the reason why you want it to be bounded away from 1 over 2 to the n is that you can kind of always get 1 over 2 to the n by just random guessing without storing anything about psi. And for those of you who know a thing or two about sampling-based quantum supremacy, you might recognize this. This is essentially the linear cross-entropy benchmark that was used in random circuit sampling. So we're really just repurposing the same thing here, but in this kind of storage sense. And I guess you could think of it as a kind of distributed version of linear cross-entropy benchmarking, where at the start you get a description of the state, and then later you get a description of the measurement basis in which you want to pass the linear cross-entropy benchmark. And kind of the key theorem that we show is that if you want to solve this task using classical storage, then you need an exponential number of bits in order to achieve a large linear cross-entropy fidelity. In particular, if the state psi and the circuit C are like literally random quantum states and circuits, then the amount of communication you need scales as something like 2 to the n. I guess specifically it's the lesser of epsilon squared times 2 to the n, or epsilon times 2 to the n over n, where epsilon is the linear cross entropy. And I guess one thing I should note, so it's a calculation that you can do that is essentially identical to the calculations that like Google did, that if you were to run a noiseless quantum computer, then you would expect to achieve like a linear cross entropy score of epsilon roughly 1. And conversely, like I said, if you just guess randomly, you'll achieve epsilon roughly 0. And in fact, actually, you kind of expect that the linear cross entropy score for sufficiently random states and circuits should be kind of correlated with the fidelity of the device. And so what this lower bound is saying is that as long as the fidelity of your device is large enough, then spoofing the outputs of this device under this sort of distributed linear cross entropy benchmark requires a lot of storage. Any questions about this?
Is there like a sentence or so you can say about why you'd expect to see 2 over 2 to the n in a random case?
I'm tempted to say no. I mean, it's kind of just like it's an integral. Like I don't know. I mean, it has to do with like the posteriors of the Dirichlet distribution, if that means anything to you. But yeah, I think that's the best intuition I have.
So somehow it's just the variance of its distribution over something.
Yeah, I mean, like essentially what happens is like there's a sense in which the measurement distribution will be like a uniformly random probability vector, which is this Dirichlet distribution. And then like, seeing something that is sampled from that probability vector, you're somehow more likely to see something heavy. And why it turns out to be exactly 2 over 2 to the n, you kind of just have to calculate. Yes?
Could you say a little bit about how this is bypassing some of the reasonable doubt that you raised earlier about the Google result?
So this is an unconditional theorem. So this does not rely on any computational hard disk assumptions. This is just something that you can prove. And that is the sense in which this is unconditional. Yeah.
But the C and the C is probably not R random, right? Because you're going to have to.
I'll get to that.
Okay.
Yeah, okay, so actually, in fact, that is the next slide. So talking a little bit about how we actually implement this. So yeah, how do we do this? In order to realize this, there's I guess, 2 parts to this experiment. So we have to be able to prepare a Haar-random quantum state with kind of the best fidelity possible, and then we have to be able to do a Haar-random measurement. So how did we do this? For the Haar-random state preparation, so it turns out there are algorithms off the shelf that will just take any quantum state and produce a circuit that will prepare it. But it turns out we found that kind of a heuristic approach to this worked much better, where what you do is essentially something sort of like a VQE, where you take a parameterized quantum circuit. So you fix a bunch of gates that are parameterized by some angles theta. And then you sort of run a sort of a gradient descent or some sort of optimization on these parameters to maximize the fidelity of this quantum circuit with your target state that you are trying to produce. One of the nice things about this is that you can also kind of incorporate the noise model of the quantum device into the output fidelity, because actually on trapped ion devices, they kind of have this feature that in some sense, the error probabilities are proportional to the angle at which you're rotating. So you can sort of estimate the amount of error that your quantum computer will accumulate while running the circuit. And by doing this sort of optimization, I guess I personally found it pretty remarkable that for 12 qubits with about it turns out 516 entangling gates, we were able to prepare states with about 46% fidelity with truly Haar-random states on a quantum device. And again, I think this is really remarkable because, again, a 2 to the 12, a 12 qubit state that's 2 to the 12 complex numbers, but just with a few hundred entangling gates, you can already get to almost 50% fidelity. And that's with the noise of the device. If the device were noiseless, I think this would be even closer to 80% or something. And then for Zeph's question, so how do you do the Haar-random measurement? So it turns out the answer is actually you can't do a high random measurement. That's too hard. So the reason is that preparing a high random state, that's like kind of doable because that's like 2 to the n gates. But doing a high random measurement is much harder because that's 4 to the n gates. So you actually can't do this. But what you can do is a random Clifford measurement. And it turns out that you can actually prove a version of the lower bound I had on the previous slide when the measurement is not high random but is rather Clifford. And the lower bound is only slightly weaker. I think actually at the parameters of the experiment, the bounds differ by a factor of about 40% or so. So it's really not too bad. So you lose something, but the point is Clifford circuits are much easier to implement. In fact, the way we did it, it turns out there's a rather nice canonical form that you can do any Clifford measurement in the following form. It's a layer of Hadamard gates, a layer of controlled Z gates, S dagger, Hadamard, and X gates. So just 5 layers of gates where only one of these layers is actually entangling. And then just by controlling these gates with classical controls, you can implement any Clifford measurement this way. And this uses up to I guess 66 entangling gates on a 12-qubit experiment. And I guess on the device, we expect to be able to implement this with about 96% fidelity. Yes?
What's your theoretical bound?
Good. So if we go back here, it's essentially the same as this, except this 2 to the n here, on this epsilon times 2 to the n, it will change to, I guess it'll be an epsilon times 2 to the 1 minus little o 1 times n. So there'll be a little low factor in the exponent that you lose, but that's it. So it's still basically 2 to the n. OK, good. So yeah, this is how we implemented it. These are essentially the circuits we ran. I can, I guess, finish up by telling you the results. So essentially, all of our results can be summarized in this one figure. So this plots the number of bits of classical communication that you need as a function of the linear cross entropy. And so this purple shaded region on the bottom, that is the region of infeasibility. So that is where we have a lower bound, showing that if you want to achieve that linear cross entropy score, you need at least that many bits of communication to replicate the 12-qubit experiment. Conversely, something I didn't talk about, but what you can actually show is an upper bound on the amount of communication. So that's what this green shaded region is on the left. We can actually show that with not too many more bits of classical communication, you actually can simulate the quantum experiment. And then finally, this line in the middle is the linear cross entropy that we observed with, I guess, 5 sigma confidence bounds. And if you look at where these curves intersect, what you conclude is that to replicate what we did in the experiment, you would need provably at least 62 bits in order to 62 bits of storage in order to get the same linear cross entropy. But our lower bounds are not tight, so it's conceivable that you might have needed, I guess, as much as 382 bits in order to replicate this. So I guess the true optimal answer lies somewhere between 62 and 382. And yeah, I can also say a little bit about some of the future directions. One of the most natural ones is just, can you close this gap? Can you either tighten the lower bound or tighten the upper bound to really get a very tight separation between quantum and classical communication? I will say that I strongly believe that one can do better than what we did, but there's probably some limit to what is provable using current techniques, because it turns out that there's some sense in which both the lower bound and the upper bound feel essentially high-dimensional sphere packing problems. And what is the densest that you can pack spheres in very high dimensions? And that's kind of just a general unresolved problem in mathematics. So this might be hard for reasons that have nothing really to do with quantum mechanics. I guess another natural question is whether you can get better separations using better hardware. So kind of the limiting factor really does seem to be this 2-qubit gate fidelity. And as you push that down, you should be able to expect to get better than 12 versus 62 separations. I think it would be nice if you could get separations where a quantum device with like a few dozen qubits is provably requiring like thousands or millions of qubits. And then maybe lastly, the last thing I'll address is one of the nice things would be to kind of close some of the loopholes in this experiment to the extent that one is viewing this as a test of quantum mechanics. So we're sort of arguing that this experiment is proving that if nature was secretly holding a classical description of these quantum states, then these quantum states would have to be complex. But just as like the earliest demonstrations of Bell inequality violations had some loopholes to them, so too does our experiment have the possibility of loopholes. And indeed, one of them is very analogous to what some of the earliest Bell inequality experiments had, which is the settings independence loophole, which essentially just says that like, so when we ran these circuits, we didn't actually generate the random Clifford measurement on the fly. So it was actually kind of generated before the experiment was run. And it was stored on some sort of microcontroller or computer that was like a few meters away from the quantum computer. But like, in principle, one could believe there's like some cosmic conspiracy where that data could have been leaked into the quantum computer before the state was prepared. And so, you could envision doing better experiments that, for instance, close this loophole by having the ability to adaptively update your measurement based on randomness generated on the fly. And yeah, I think that's everything I wanted to say. I'm happy to stop there and take questions.
You said that you used 12 qubits. Why not 20?
Good. So it sort of turns out that to get the optimal separation, there's in some sense you want like your number of qubits to be basically the log of, what is it? The log of the of 1 over the 2-qubit gate fidelity or something. So yeah, it's just because like if you wanted to prepare Har-random 20-qubit states, you would be doing that with much lower fidelity than you can prepare Har-random 12-qubit states. I should note there's not like some theoretical formula. It's just empirically we found that 12 seemed to give us the best separation we could get.
Hi, thanks for the talk. So essentially what you showed here, right, is that information theoretically, you can say in some sense n qubits is stronger than n bits. But I guess for these supremacy type experiments, right, the ideal that we would want is like information theoretically, the current quantum hardware we have today can outperform the current like classical hardware we have today.
Oh, sure. And I mean, I think in some sense you're never going to achieve that with something like this.
That was sort of my question was whether you think some, like it doesn't have to be this experiment, but any sort of like type of, information theoretic argument could be scaled up such that the classical lower bound would be, many trillions of classical bits.
So I'm not going to say that can never be done for any experiment of this type, but like one of the fundamental limitations of doing something like this is that the circuit that you write down to prepare the state is always a sort of classical description of the quantum state that gives you a classical attack. So like, so in order to run an experiment like this, we're always going to need classical control hardware that is at least as large as the number of bits for which we want to show a lower bound. So at least, yeah, I mean, like I said, this is not. We never claim that this is infeasible for classical computers. So it's sort of not the point of the experiment. It's just a separation between quantum resources and classical resources.
Sorry, but couldn't you just have your quantum circuit prepare the state and then transmit it somewhere else, hold it there, and then have that be queried? So
I mean, sure. If you could, it would be nice to demonstrate this using sort of communication between two devices, so that you can just say that like I don't know if it's like photons or whatever you're sending between the two devices. You can say at least those photons had to have a large classical description. Maybe that would be like a more convincing demonstration. Because I mean, I think one of the objections people have raised against this is that, like, in some sense, shouldn't you be counting all of the classical control hardware in your count of like the number of qubits in the system? I mean, maybe. I think that's reasonable, and the way you could close that loophole is, I think, like Umesh proposed, using something involving communication between two parties.
Thank you.
Thanks.